Usually when we talk about seeing the future, there's this expectation of magic, right? You picture a crystal ball. You stare into the cloudy glass, and suddenly you know exactly how things are going to play out before they even happen. It's, purely the stuff of fantasy novels.
Right, yeah. I mean, the ability to predict the physical future of matter without ever actually touching it, it just seems impossible. It completely defies common sense.
Yet you have actually probably been staring at a real working crystal ball since you were like 14 years old.
Mm.
It wasn't made of glass, and it was probably tacked to the cinder block wall of your high school science classroom.
Oh, absolutely. The poster everyone ignores.
Right. So welcome to today's deep dive. Our mission today is to completely change how you look at the periodic table of elements. We're going to look at some excerpts from an essay that reveals this isn't just a reference chart or a list of stuff you have to memorize for a quiz.
No, not at all. It's a predictive map of matter. It's literally a cheat sheet for the entire universe.
It's wild to think that a simple grid on a classroom poster can actually tell you how a piece of matter will behave or, what it'll react with before you even conduct a single experiment.
Yeah, and to really appreciate how this scientific crystal ball actually works, we have to kind of travel back to the mid-1800s. We have to look at the absolute chaos that chemists were dealing with back then.
It was bad, right?
It was a mess. At that time, chemistry was essentially this massive, frustrating jigsaw puzzle, and, well, half the pieces were just missing. Scientists had identified about 60 individual elements.
Okay, so 60 pieces on the table.
Right. And they were measuring them. They knew each one had a characteristic atomic weight, and they observed certain chemical reactions. But nobody had managed to assemble a single coherent scheme that worked across that entire set of known elements.
So it's basically a pile of puzzle pieces with no picture on the box to guide you.
Exactly. I mean, several scientists noticed partial patterns. They saw that certain elements formed little families with similar behaviors, but those patterns always broke down when they tried to apply them to the whole group.
And this is where Mendeleev steps into the mess.
Yeah.
This is 1869.
Yeah, 1869. Dmitri Mendeleev decides to arrange all these known elements purely in order of their atomic weight. And when he lined them up by weight, he noticed something really profound. The chemical properties of the elements repeated at regular intervals.
Oh, hence the name periodic. Like the behaviors appear periodically as you move down the line.
You got it. So he took this long single-file line of elements and he broke it into rows. Then he stacked those rows on top of each other so that elements with similar chemical behaviors lined up perfectly in vertical columns.
I mean, that seems like a pretty reasonable way to organize data. But the source text we're looking at highlights that Mendeleev made two incredibly bold decisions here to make his specific version work, right? Because everyone else's had failed. Because when he was ordering them by weight, he sometimes found that an element landed in a column where it clearly didn't belong chemically. Like it just didn't act like the other elements in that vertical family.
And his solution to that problem was just sheer audacity. I mean, he assumed the measured atomic weight had to be wrong.
Wait, really? He basically told his colleagues, hey, your hard-won laboratory measurements are incorrect because they ruin my nice pattern.
That's exactly what he did. He just moved the element to the column where its chemical behavior dictated it should be.
The nerve that takes. To tell the entire scientific community that your unproven visual pattern is more accurate than their literal physical scales. It's wild. How on earth did they accept a theory with holes like that?
Well, initially they didn't, but he was right. The chemical behavior, like how the element actually interacted with the world, was a deeper, more fundamental signal to follow than just its weight. And his second decision was even more mind-blowing.
Right, the gaps.
Yeah. When his pattern demanded an element with specific properties, but nobody had ever discovered such an element, he didn't just force a known element into the spot. He just left an empty gap in his chart.
But he didn't just leave it blank, right? He basically put a wanted poster there.
Exactly. He actively predicted the exact properties of the missing element. He predicted the approximate weight, the density, what its oxide would look like, and exactly how it would react with other chemicals.
And obviously the scientific community pushed back against a theory with giant glaring holes in it. You can't just claim that invisible, completely undiscovered elements prove your radical new organizational chart is right.
No, you can't, unless
those invisible elements actually show up.
Which is exactly what happened. Within 15 years of him publishing his table, 3 entirely new elements were discovered: gallium, scandium, and germanium. And when scientists measured the properties of these new elements, they matched Mendeleev's risky predictions incredibly closely.
See, that is the ultimate crystal ball moment. Making a risky prediction about reality and having it come completely true. That converts a mere filing system into a robust scientific theory.
Yeah, the critics were totally silenced because the chart worked. But the crazy thing is, Mendeleev is operating entirely on observation. He sees the pattern, but he has absolutely no idea what the physical machinery is that's actually driving it.
Right, the why of it all.
Exactly. The physical reason his columns worked was completely invisible to him. That underlying mechanism wouldn't be discovered until the early 20th century, deep inside the atomic structure itself.
It turns out the entire map is driven by the literal anatomy of the atom.
It really is.
Let's actually look at that anatomy for a second. If we zoom in on an atom, there's a dense core, right? The nucleus. And that contains positively charged protons and neutral neutrons. And then surrounding that nucleus is a swarm of negatively charged electrons.
Right. And the protons are the absolute defining feature of the element. The number of protons is the atomic number. Carbon, for instance, always has exactly 6 protons. Always. If you add or subtract a proton, you don't just get an altered version of carbon, you have forged a completely different element.
Which quietly fixes all those little anomalies Mendeleev had to fudge, right, about it.
Yeah.
When he was guessing the atomic weights were wrong. Because the modern periodic table is actually ordered by this proton count, not the weight. The protons were the hidden sequence all along.
Exactly. But while the protons dictate the identity of the element, the electrons dictate its personality.
Oh, like that?
Yeah. The electrons tell you how the atom is going to behave in the real world. The electrons arrange themselves in layers or shells around the nucleus. And the golden rule of chemistry is that each of these shells can only hold a very specific, limited number of electrons.
Right.
An atom's chemical behavior is governed almost entirely by its outermost shell.
Okay, so picture these electron shells like seating arrangements at a highly stressful dinner party.
Oh, that's a good way to look at it.
Yeah, it's like these atoms are desperately trying to fill their outer tables so they can finally relax and have a stable, low-energy evening. And how far they are from achieving a full table dictates how erratically they act.
They hate having empty seats.
Right. If they're just one guest short of a full table, they are going to be frantically pulling people in from the street to fill that seat.
Yeah, atoms are constantly trying to achieve that full outer shell. It represents a stable, low-energy state. How far an atom is from that goal determines absolutely everything it does.
So because an atom's desperation to fill its outer shell drives its behavior, the physical layout of the periodic table suddenly makes perfect mechanical sense. Reading the map through this lens kind of changes everything.
It really does. Because a horizontal row, which chemists call a period, represents the gradual filling of one of those shells. As you trace your finger from left to right along a row, you're just adding electrons one at a time until that specific shell is completely full.
And once it's full, you drop down, a new row starts, and a brand new shell begins filling up around the old one.
Exactly, which inherently means a vertical column. A group collects all the elements that have the exact same number of electrons sitting in their outermost shell.
Ah, so because that outer shell configuration drives the chemistry, elements in a vertical column behave incredibly similarly. It isn't a coincidence that they line up at all.
No, it's the fundamental mechanical reason for the arrangement. Let's actually walk through the extremes of the map to see this in action. Look at the far left column.
The alkali metals. We're talking about lithium, sodium, potassium.
Right. Every single one of them has just one lonely electron sitting in its outermost shell. They are exactly one electron away from emptying that partial shell entirely and just falling back to the perfectly full, stable shell beneath it.
Oh, so it is significantly easier for them to just kick out that one extra dinner guest than to try and scavenge 7 more electrons to fill the current table.
Exactly. They give that electron up eagerly. And in the world of chemistry, eagerly usually means violently.
Yeah, dropping a chunk of pure sodium into water doesn't just create a mild fizz, right?
Right.
It aggressively tears the water molecules apart, it releases hydrogen gas, and it generates so much heat that the hydrogen literally catches fire.
It's explosive, and that reactivity actually increases as you move down the column. Potassium is more dramatic than sodium. Cesium is practically explosive just sitting there.
Why does it increase as you go down? Oh, because as you move down the column, the atoms are getting physically larger, right? They have more completed shells layered inside.
Exactly.
So that means that single, lonely outer electron is sitting physically further away from the pulling force of the positive nucleus. It's less tightly held by the magnetic pole, making it even easier to just lose it.
You nailed it. The ease of losing that electron translates directly to increased chemical volatility. Now, contrast that violent desperation with the far right column of the table.
The noble gases.
Yeah.
Helium, neon, argon.
Right. They have completely full outer shells. Their dinner tables are entirely booked. No empty seats.
So they're just completely aloof. They have nothing to gain by taking an electron and absolutely nothing to lose by giving one up. They barely react with anything in the universe.
Yeah. And this structural aloofness is why helium is perfectly safe to use in children's party balloons, whereas hydrogen, which sits on the far left and only has one electron, is famously flammable and dangerous.
Oh, the Hindenburg.
Exactly. It's also why museums pump argon gas into display cases to preserve delicate ancient artifacts. The argon pushes away the highly reactive oxygen and does absolutely nothing to the artifact itself.
Okay, so what about the ones right next to the noble gases? The halogens. Chlorine, chlorine, bromine, iodine. They sit just to the left of the noble gases, which means they are exactly one electron short of a completely full shell.
Oh, they're the ones aggressively grabbing people off the street.
Yes. The periodic table is essentially functioning as a dating app. Like, sodium is desperate to lose exactly one electron. Chlorine is desperate to gain exactly one electron.
They're a perfect match.
They're a match made in heaven. Their chemical neuroses perfectly complement each other.
Yeah, an element desperate to lose an electron paired with one desperate to gain an electron produces an incredibly stable compound. Sodium plus chlorine gives you everyday table salt.
Which is crazy to think about. Two highly reactive, potentially lethal elements locked together in a perfect energetic embrace to make something you just happily sprinkle on your fries.
It's amazing. So the vertical columns dictate the chemistry, right? But there are broader geographical trends running across the entire map that dictate the physical materials we actually rely on every day. There's a distinct pattern in the physical size of the atoms themselves.
And the physical size morphs in a way that actually feels deeply counterintuitive. As you move from left to right across a single row, the atoms generally get smaller.
Which sounds wrong, right? You're adding protons to the nucleus and adding electrons to the outer shell as you move right. You would just assume accumulating more particles means a larger atom. But those new electrons are being crammed into the exact same shell. Meanwhile, the nucleus is getting more positively charged with every single added proton.
Ah, so that stronger positive magnet is naturally going to pull that entire electron shell inward.
Exactly. The increasing nuclear charge acts like a winch. It just tightens the radius of the atom. Conversely, as you move down a vertical column, the atoms get larger because you're adding entirely new shells, wrapping layer upon layer around the core.
The map also divides into distinct material neighborhoods, too. Metals occupy the left and the sprawling center of the table. Non-metals are huddled up in the upper right corner.
And sitting right on the geographic boundary between them is this diagonal band of elements called the metalloids, things like silicon and germanium.
And they sit perfectly on the border between the metals which readily conduct electricity and the non-metals which do not.
Right, and because they sit on that geographic boundary, their physical properties are also boundary-like. They can conduct electricity under some very specific conditions, but they act as insulators under others.
Which makes them perfect semiconductors. They literally form the entire physical foundation of modern computing and electronics.
Yep, Silicon Valley is named after geography on the periodic table.
That's a great point.
Yeah.
But looking at the standard map, we do have to talk about the basement.
Ah, the basement.
Yeah, there are always those two detached rows just floating awkwardly at the bottom of the poster, the lanthanides and the actinides.
Yeah, they actually belong inside the main table. The only reason they're exiled to the bottom of the poster is a compromise for readability.
Really?
Yeah. If you inserted them where they actually belong mathematically, the table would become incredibly wide. It would be super inconvenient to print on a standard piece of paper.
Wait, so we literally tore the bottom off the map for aesthetic convenience, so it fits on a standard poster. Doesn't that obscure how the universe actually structures itself just to appease, like, graphic design?
It does feel like a strange scientific compromise, yeah. It's a formatting quirk. But those floating elements are absolutely vital to modern life. The top floating row, the lanthanides, are frequently referred to as the rare earths.
But they aren't actually rare.
No, they're not really rare in the Earth's crust, but they share an incredibly similar outer shell electron configuration,
Which means they behave almost identically in chemical reactions.
making them a massive headache to separate from one another when they're mined together. They're just really awkward to process, which is exactly why they are a massive strategic supply chain concern globally.
Right, because humanity completely relies on them for, well, everything. High-powered magnets, advanced batteries, the screens on our devices.
Everything. But while those bottom rows stretch our formatting limits, the far right edge of the table stretches the physical limits of reality itself.
Because element 92, uranium, is the end of the naturally occurring map. Everything beyond uranium has to be artificially forged.
Right. Scientists create these super heavy elements in laboratories. They basically accelerate one nucleus into another at phenomenal speeds, just hoping they fuse together rather than shattering.
And these super heavy elements, which currently stretch out to element 118, oganesson, they are wildly unstable. The source material notes that many of them exist for mere milliseconds before they completely fall apart.
Yeah, some of these elements have only ever been observed a handful of atoms at a time. You can't run traditional chemistry experiments on them.
Because by the time you tried to observe them interacting in a beaker, they'd have already ceased to exist.
Exactly. Their chemical behavior has to be entirely inferred using the predictive logic of Mendeleev's map. Stacking positive protons indefinitely inherently creates a massive electrostatic problem.
Right, because positive charges naturally want to violently repel each other. It's like trying to force the north poles of two really strong magnets together. At some point, the nucleus should just blow itself apart.
And the electrostatic repulsion does eventually become completely overwhelming. There is a fundamental force called the strong nuclear force that binds the protons and neutrons together, and it actively fights against that electrostatic repulsion.
But the strong nuclear force has a severe distance limitation, doesn't it?
It does. It only operates over extremely short distances. It can only really hold on to the particles immediately adjacent to it. So as the nucleus gets bigger and bigger with more protons crammed in, the long-range electrostatic repulsion pushing everything apart eventually overpowers the short-range strong nuclear force trying to hold it together.
And the atom just instantly rips itself apart.
Exactly.
So pragmatically speaking, if these super heavy elements only exist for a millisecond before they blink out of existence, why do we even bother slamming them together? What is the point of discovering something you can't even hold or study? It feels a little abstract.
It's a fair question, but it's about rigorously testing our understanding of the fundamental rules of matter. If our mathematical theories predict an element will last for exactly 2 milliseconds and decay in a highly specific way, and then we build it and it performs exactly as predicted.
It proves our fundamental understanding of the universe is correct.
Yes. Plus, the pursuit is driven by a tantalizing theoretical possibility.
Oh, the elusive island of stability.
Right. Theoretical physics suggests that if we can reach certain highly specific combinations of protons and neutrons, we might find an island of stability further out on the map. A grouping of super heavy elements whose internal geometry is balanced just right, meaning they might not decay in milliseconds, they might stick around.
But we struggle to reach it because creating nuclei with the specific, highly neutron-rich combinations required is just technologically agonizing.
It is, but if we can map these extreme, fleeting states of matter, it really grounds the rest of the chart in a profound reality. These elements are not abstract categories. They are physical artifacts with distinct cosmic origin stories.
And that's the thing that really brings it all home. Every single element has a specific manufacturing origin in the cosmos. Hydrogen and most of the helium in the universe were formed in the extremely hot, dense conditions of the first few minutes after the Big Bang.
But the Big Bang couldn't manufacture the heavier elements. Those required the internal foundries of stars. Elements up to iron, which is element 26, were forged by the immense crushing pressure of nuclear fusion inside the cores of stars.
Because the gravity pulls inward so fiercely that it overcomes the electrostatic repulsion, right? It forces the lighter elements to fuse together.
Exactly. But stellar fusion hits a dead end at iron. Fusing iron doesn't produce outward energy, it absorbs it. So the star collapses. To create the heavier elements, you need extreme catastrophic violence.
Like supernovae.
Supernovae and the massive collisions of incredibly dense neutron stars. They provide the raw kinetic force needed to smash lighter nuclei together to create the heavier elements on the periodic table.
So when you look down at your own hand, the gold in your jewelry, the iodine regulating your thyroid gland, the calcium providing the structure of your bones. None of it is random matter. Each of those specific atoms was manufactured somewhere specific in the cosmos, under extreme conditions that science can accurately describe.
You're literally looking at a cosmic collage of Big Bangs, dead stars, and explosive galactic collisions.
The periodic table is actually a history book of the entire universe.
It tracks the evolution of matter from the dawn of time right down to the device you're using to listen to this conversation.
It really is a predictive map of matter. It's ordered precisely by the proton count, it's structured by the rigid rules of electron shells, and it's readable in both directions. You can look at where an element sits and instantly know how it behaves. Or you can observe how something behaves and know exactly where it must live on the map.
And Mendeleev built the foundation of this map purely through observation, without even knowing that protons or electrons existed. Yet his framework was so robust that it confidently predicted the unknown.
It's brilliant.
It is, and the true magic of this map is that it still contains uncharted territory. I mean, think about it. If humanity ever does navigate to that theoretical island of stability we talked about and figures out how to forge those stable, super heavy elements with the perfect neutron mix,
What completely unimaginable materials or technologies might we unleash into the world? Things that have literally never existed anywhere in nature.
exactly, entirely new realms of science.
Well, thank you for joining us on this deep dive. Next time you happen to walk past a science classroom, take a second look at that poster on the wall. It's not just a list of stuff to memorize. It's a crystal ball, and it's predicting the physical future of everything around you.